Okay, I want to go over some more voltage drop testing today, but before we do, I need to prove a couple of concepts to you guys. The first one is every part of the circuit has resistance. If that wasn't the case, if we had a completely dead short from the positive to the negative on a battery, this wire would not get damaged. If this had no resistance whatsoever, what would happen is we'd connect this and all it would do is drain the battery flat. It would just transfer all of the current and all of the voltage from one side to the other, equalizing it, and then there would be no more juice, no more power, right? Well, that's not the case. We know through testing, and we're going to prove it here, that every part of a circuit has some resistance, even if it's very, very low resistance. Like if I take a ohm meter and go across from here to here, it's going to read zeros, but it's not really zeros. It's a very, very low resistance, and we're going to prove that it has resistance because the more current that flows through this wire, the higher the voltage drop is going to be from here to here, and this is going to get hot. The reason this gets hot is because it's resisting current flow. Just like anything that gets hot with current flow, the reason it gets hot is because it's consuming power and resisting current flow. And we're going to watch that happen now. I don't know if I can actually make it start on fire. Huh. It won't start on fire. Damn it. So it's going to happen fast because that's what happens when current flow is uncontrolled. But I want you, so this is going to be grounded out because the clamp is over here on that. So when I hold that down, that wire is getting really hot. We'll probably see it start smoking. Probably should have taken a second and shine that up, but you can see that's pulling as many amps as it can, as much current through that wire as possible, and the whole wire is getting hot. The reason the wire is getting hot is because it's reaching its maximum current potential. And we could use that to our advantage in testing because that proves that all wire has some resistance, even though it might not be measurable with conventional tools. I hope that gets my point across. Otherwise, we could definitely use some small wires to start a fire, but I think you get the point. That's going to carry current until it can't. You can see it just start on fire. That's the same way a fuse works. So that's what we're going to use that, one of those, this is one of the concepts that you need to understand, that no matter what, there is resistance in this wire. Even though it seems like zero, that's not the case. It has some resistance, and the more current flow that flows through it, the more the voltage is affected by that resistance. And we're going to demonstrate that with some other tests, but I just want you to understand that every single part of the circuit has some resistance, even though it may not be measurable. But let's move this around and try to start it on fire anyway. Let's see if we can touch it right to the negative. Oh, and don't try this at home. You can see it just burnt the end of it off, just like a welding rod. That's what you're doing when you're welding. You're just putting high current through there. The rod's the weakest point, or that's going to maintain really the rod when you're welding is what can't handle the current. It melts, and that's how you can weld with it. But that's how we just burnt the end of that wire off. So just want everybody to understand that that has resistance in it. And in this case, if we're just shorting the wire straight to ground, this is going to be what's limiting the current. But in a regular circuit, there is still some current being limited by this wire, and that we can measure that by measuring voltage drop. I know I'm kind of beating a dead horse here, but it's really important that you understand that every single part of a circuit, no matter what it is, whether it's a connector, a wire, or a terminal end, or a crimp, they always have some resistance. Now, it might be hard to measure that, but we can measure that using voltage drop, and I'm going to demonstrate that here over the next 20 minutes or so. So we're gonna cut this and go to a different setup and another demonstration of another concept that's extremely important before we get into voltage drop measure. So the first concept is all parts of the circuit have some resistance, will consume some energy, therefore will consume some voltage during a complete circuit or under load. So it's going to, the voltage consumed from one end of a wire to another represents the amount of energy that it takes to move the current and the voltage through that wire. And hopefully I can demonstrate that and make that make sense to you. But the main thing you need to remember is everything has resistance. Every single part of a circuit has some resistance, which causes some current limiting effects, which can be measured in voltage drop. So now we're going to go on to the next concept here. All right, the next concept that I would like to demonstrate is a multimeter. A lot of people call them voltmeters, DVOMs, DMMs, whatever you want to call them, multimeter. The best way to call them, or what I call it in my head when I'm measuring strictly voltage, is a subtraction meter. And that can be a tough concept to understand, but it's really important to understand that we're not measuring voltage at one point when we're using this. We're not grounding it and then measuring voltage at one point. What we're doing is we're measuring voltage at this point and then voltage at this point and subtracting the negative from the positive to get a total voltage potential. So the potential between the 2 points, which is the positive minus the negative, equals the potential in voltage, or the difference between the two. So that's why I call it a subtraction meter, because if I'm going to measure here, which is right off the battery, and I'm going to measure over here, which is right off the battery, I get 12.53. Now that doesn't mean the battery's got 12.53 volts. What that means is the difference in potential from the positive post, or in this case the jump pack, from the positive lead to the negative lead, the difference is 12.3 volts. How much current can that carry? I have no idea, because I'm only measuring the difference between the two spots. I hope that makes sense. And then, so the best way, this is how I understand it. I used to have a analog voltmeter, but I don't anymore. I may actually pick one up sometime for a demonstration, but for today, we're going to use this battery load tester, which has an analog meter on it. And this doesn't take any batteries. There's nowhere to put batteries inside this thing. And the reason it can still work is, years ago, before fancy digital multimeters, we only had analog meters. And how they worked is they had an extremely high resistance from the positive to the negative. And what happens is it uses a very, very small amount of current to move this needle wherever it needs to go. And where the needle goes depends on the difference in potential from the positive to the negative. So not necessarily how much current can flow, but how much pressure or voltage is there. the amount of pressure on the positive lead drives the needle high. If the difference between the two is 0, it stays on 0. If there's more pressure on the positive lead, then the needle points to how much ever pressure or voltage it's creating, or it's measuring, really. So it's measuring the difference between the two. So you can imagine this is just a little motor that responds to the amount of voltage between the positive lead and the negative lead. So and here we'll just demonstrate quick. If I can get the lead to grab it, there we go. Now I'm gonna go over here and grab this one. Actually, you know what? I'll set it down because I'm running out of hands. So now we have a difference in potential of 12 volts. And there's actually a small amount of current flowing here, but that's the nature of most multimeters. Well, really, pretty much all multimeters are gonna flow a very small, almost immeasurable amount of current through there to determine the amount of voltage between the 2 points. It doesn't mean anytime you put this on 12 volts, it's gonna read 12 volts, and we're gonna get to that later. But for now, what you need to understand is all voltmeters are actually only subtraction meters. They only measure the difference between the positive and the negative. That's super important to understand, and you'll see why here in a minute. And we're just going to start with some very basic circuit testing and voltage drop testing across them. But remember, every time you're using a voltmeter, you're doing a voltage drop test. These are 2 open leads right from the battery. This is the positive lead, this is the negative lead. I'm going to go ahead and clip my lead on there. I'm going to clip this lead on here. I have 12.3 volts. Make sure you can see that good. All right, I have 12.3 volts across here. Now, what is going to happen when I connect my headlight? Well, because we're running a battery, we may have the voltage drop at the battery, which is a different type of voltage drop. I'm actually going to put these down so I can get to them a little nicer. Okay, so if we measure across the 2 points at the component, we have 11.81 across the component loaded. Is that good or bad? Well, I don't know, lights the light bulb, must be good, right? Well, it is good. Lights the light bulb. If I was to measure across here and I didn't have any complaints of dim light bulbs and everything, and I knew I had a battery that wasn't being supported by a maintainer or a charging system, this is probably okay. But how do we know for sure? Well, let's verify our circuit. We're gonna assume, knowing that this wire has resistance, we're gonna assume the voltage will be lower at the positive connection at our component than it will be at our battery. So now, I'm going to put our negative lead here because it's the lower of the 2. I'm gonna put my positive lead way up here. And you can see our meter is reading 160 millivolts. So we have 160 millivolts of drop through that wire to the component. And that's perfectly acceptable, obviously, right? But where is that voltage going? Why are we losing that? Well, we're losing that voltage in the form of power consumption through the resistance from here to here. That's where the voltage is going. It's being consumed because that's the amount of power it takes to go from the positive here to here. Now, we could get into electron theory and everything else, but just so it makes sense in your head when you're doing testing, just follow my logic and follow how I'm breaking this down. So the difference in measured voltage proves that there is some power being consumed across here. So we know across these two leads, well, now since it's getting warmer, it's going up. We're at 187 millivolts. So if we were going to test the ground side from here to the battery ground, which I have slightly out of frame, you'll have to forgive me for that, we're going to get some kind of reading because there's some power being consumed there. So we want to put our positive lead at the highest presumed voltage. And in a circuit that's working completely, if we're going to do a voltage drop test on the ground side, we're going to measure from the ground at the component to the ground at the battery, and we're measuring about 158 millivolts. And what that proves is not only is the circuit integrity good, we know that because the component's working and everything, but again, it's demonstrating that this wire has some resistance. And we could use Ohm's law to find out the exact resistance of that wire, but we're not gonna because we don't care, because this component is function. Now, I hope that all makes sense. And then again, you know, we can do voltage drop testing in multiple different ways. Sometimes it doesn't make sense to do end-to-end testing, like from the battery positive to the positive of the component, which is how this test is commonly taught, right? We have 180 millivolts of drop across there. But we're doing voltage drop testing also if we just go across the component. If we go across the component, we're at 11.77 volts. Now, if we open this circuit, here, let's just open the circuit at the ground. So we're going to take the ground off. Now that the circuit's open, we're going to measure across here. We have 0 volts, right? Because it's open at the ground. So how many volts do we have here? Now think about that for a second. There's 12 volts coming out of the battery, all the way through this circuit, all the way through here, through this wire to here. This open connection is stopping the current flow. So if we put our positive lead here, assuming that we know this is open, and then we touch our ground at our battery, we have 12.4 volts. So now we know we have a ground here. We're going to take this off at the component. So now we have basically an unplugged component again. Okay, so now we know the voltage is coming out of the battery through this wire to here. And we know, because we did our voltage drop test, that from here to there is good. When this is all connected, we have 11.77 volts. So if we connect our leads to it, we have 12.41. Now, if we wanted to, we could take and write, 12.41, 11.77. We can, minus that from that and get our total voltage drop on our circuit. I hope that makes sense. So we want to get our total voltage drop on our circuit. All we have to do is be at our component. We don't even really need to be at the, we don't have to be at the battery and at the component. And that's where I think a lot of voltage drop testing explanations kind of fall short. We don't have to do voltage drop testing end-to-end from the positive to the positive. What we do need to do is, with the circuit unloaded, we know there's no current flowing. So we know the resistance in the circuit isn't affected by current flow. So we know we can measure across, we can measure across the positive and the negative at the component, and we get battery voltage, right? So battery voltage is 12.43. When we connect our component back up, now we're adding another variable, which is current flow. So if we have 12.43 with no current flow, and then we measure across those terminals with the component installed, we have 11.81. So our total circuit voltage drop at our component is the 12.43 minus the 11.81, which is, you know what, so let's say 500 millivolts. Is 500 millivolts a big deal? In this case, we know it's not. The headlight light's bright, 500 millivolts is acceptable. I'm not worried about it. I'm moving on. Car has no concern at this time. But what if it does have a concern? So we're going to create a concern with this bulb. We're going to use this as a simulated resistance in the circuit. And I don't want to confuse you guys, but I am going to put this on the ground side of the circuit to demonstrate this point, because oftentimes when I get hired to do a job that another professional has bailed on, has too much time on, a lot of times what I end up finding is voltage on this ground. And I'm going to demonstrate how we find it, and again, why we don't have to do end-to-end testing all of the time. So we're going to go over this really quickly. So I'm going to move the ground from the light. I've grounded, this is grounded at the battery, okay? So then the ground from the light is going to get connected to this bulb. And this bulb is really bright. This is going to be not bright at all because this light takes a lot more current to flow. So I'm going to take this off of here and that off of there. And this is our ground, or this is our presumed battery ground, because the diagram shows that this goes directly to ground. Even though this is a simulated resistance on the ground, this is our presumed battery ground at our component. This is our presumed feed at the component. So now, if I measure across here, what do you think I'm going to get for volts? With the circuit unloaded, we know if this goes directly to ground and there's no current flowing, and this comes directly from positive and there's no current flowing, we should get battery voltage. And we do. 12.41. Well, what happens if we connect the positive to our component? We still get 12.41. because there's no current flowing. And you can see we have ground here. I'm going to check the ground terminal, and we still have 12.41. Even though we have the resistance of this bulb is in play, there's no current flowing, so the pressure or the current or the voltage is going to be the same if there's no current flowing, because it has nowhere for that pressure to go. So we're at 12.42 as the battery recovers. So now we're going to connect our ground to our light. And our light doesn't come on. Here, that one does. But the component doesn't come on. It'd be nice if all faults just glowed really bright like that. But now we know our light is lit brightly. But it's getting all of its voltage from battery positive through this bulb, through the ground side of the bulb, to here. So now, if we're going to measure at our component, we only have 986 millivolts available. We had 12.42 before we connected it. What does that mean? Well, that means something else is consuming all that power on the circuit, and we need to figure out what is consuming all the power that we need to light this bulb. Now that we know we have voltage drop, because I can disconnect this, measure from here to here, I have 12.35. With our component out of the way, I've got battery voltage. With our component connected, all of a sudden, our voltage goes down to, well, it's going to equalize, but let's say 1 millivolt. 964 millivolts, or close to 1 volt. So what that tells me is I definitely have a voltage drop concern on this circuit, but I don't know where it's at yet, right? Because I disconnect this, I have battery voltage, I reconnect the component, I've got 900 millivolts. So I know I have a high resistance point somewhere in a voltage drop concern. Now that I know that, now that's where voltage drop testing applies. Now I can run a lead back to the battery. Well, we're going to assume that our positive is going to be the lowest side. So we're going to run a lead back to the battery and test it. And I've got 58 millivolts of drop from the positive to the negative. So it's safe to say there's no problem from the positive on the battery to the feed at the component. I feel like that's safe to say because we only have 53 millivolts of drop, right? Well, if I put my negative lead on the battery negative and then touch the negative of the component, I've got 11.24 volts of drop from the negative on my component to the battery ground. So now I know the problem is definitely from the battery ground to the component ground. There's a problem there. So we have a high resistance point causing over 11 volts of drop from the ground side of the component to the battery while the circuit's loaded. And you can see we take that off and then measure it. We have 0 volts. That's a complete circuit. You know, if we have 0 volts like that, we don't know that we have a complete circuit, but we do know that we have no difference in potential from the connector at the component to ground until we load the circuit. And then if we measure it, we've got 11.4 volts, and it's steadily going down as that bulb heats up. So we know the problem is on the ground side. And, you know, obviously in this case, it lights nice and bright, so we know. But if we just had a resistor in there, it would cause the same issue. So now we're going to switch this to the positive side. So this is connected directly to our battery ground. We're going to go ahead and install that. And then we're going to leave this here, because I don't want to confuse you with the wrong colored wires. So I'm going to take this, there's that bulb. There's the positive going to the bulb, going to our component. We're going to add that resistance on the positive side of the circuit. And again, we're going to disconnect our component. So we have our component connector. And we're going to measure it again. Across the component connector, we have 12.38 volts. Now, I'm going to connect my ground. Still, right? I mean, normally a component connector, you're not going to be able to connect one at a time. So let's just connect them both anyway, right? And then we're going to check them across the terminals, right? So that's the first step, because I want to know. I know I've got battery voltage with the component connector unplugged, right? I checked it across the terminals with the connector unplugged. I've got battery voltage. So probably not a direct open. I know I don't have a blown fuse or something like that. But as soon as I connect the component, if I check voltage again, I've got about 900 millivolts. So that means I definitely have voltage drop somewhere on this circuit. Where is the voltage going? Well, again, once we get that far, we have to get this far. This is the most important thing to me, because chances are it's a lot easier to just disconnect the component, check voltage, like that, 12.37. You could even have these back probed. I don't know if we can get these in there, so you can just watch the voltage go away. No, not going to happen. But you could even have these back probed. You unplug them. 12.4. You connect your component back up, and then you check for voltage. across your component feed and ground, and now we're at 900 millivolts again. Well, I know I have a high resistance point again. Now this is where I'm going to do my end-to-end voltage drop testing. So now I know, I'm presuming the feed at the component is going to be my lowest voltage point on the whole feed side of the circuit. And then I'm going to take my other lead and touch it to the battery positive, and I have 11.27 volts. So I know I'm losing 11.27 volts across the positive side of the circuit. Even though, don't you wish all problems just had a nice bright light on them? But that's where I feel like it applies the most. And what's cool about this test is once you get your head wrapped around it, everything just starts to make sense. So again, you know, if I say I want to test, you know, from here, which is my feed, to here, I have battery voltage on an open wire. And now I know I have 0 volts there because they're connected. You know, so again, I really want to demonstrate that you can have a good voltage reading with the circuit unloaded. I've got 12.38 volts on an unloaded circuit, and as soon as I connect it, you know, and I'm purposely doing this without any test lights, because you can diagnose a circuit without a test light using voltage drop alone, and this is how. So we're just going to measure across the terminal with the circuit loaded, and we have 12.93. Now say I find my bad connection, right? Obviously, because it's glowing bright. And I get rid of it, and I fix it. Now our component works again. So what's our voltage drop going to be across our component? Near battery voltage, right? 11.68. So again, if you have a component that's not working, and it's easier to unplug it, so you unplug it and check your voltage. I've got 12.3 volts. So now I want to show you this with a test light to show you how this works. So say I do know I have a high resistance point, right? And again, this is why I don't typically advocate for end-to-end testing without the power probe, because the power probe is hooked to the battery. So that's nice and convenient. Otherwise, I'm going to demonstrate how I'm going to find this high resistance using just the component connector and a test light to have this all make sense to you. Okay, so I'm going to measure from my positive to my negative terminal or lead at the component. And right now I've got 1 volt. That's not enough to light my component. So I know I have a problem here. I still don't know which side it's on, and I'm not sure I care at this moment, right? So we're going to try to figure out how. So right now I know I have voltage with these off, right? I've got battery voltage. And with it connected, I have 1 volt. Well, how do I make that make sense at the connector? So at the connector, I have my positive lead, my negative lead on my multimeter. And all the other tools I have is just this test light. And the battery is way inconvenient. I don't have 30-foot of leads. I don't know how I'm going to get to the battery to test this. So that's kind of a problem. So first thing I'm going to do is get out my handy test light and just connect the test light from the positive to the negative and substitute for the component. Even though the component's a 4 amp load, this is only going to be a couple hundred millivolts or milliamps. But when I put it across the component, you watch that voltage drop. It goes from 12.4 to 12.17. But it lights my light, right? So it must be good. Now what do you do? I don't know. my component doesn't work, and as soon as I hook it up, my voltage goes away, right? Because I'm going to take these two, I'm going to touch that to that side of the light, I'm going to touch that to the other side of the light, and the voltage goes away. So I know I have a problem. This light's not enough. That's actually why I bring this with when I'm doing circuit testing, is because if I have a circuit that can handle 60 amps, like this one, I've got two 60 amp fuses up here, I know this might not be enough, but this will demonstrate there is some voltage drop there, right? And we could still do our end-to-end testing, so you can see how that could trick you, right? So even though I have this bulb in place, I'm going to put this across here, I've got 12 volts, I do have some voltage drop with a light load, but it's not even enough to do anything, right? See that? It goes from 12.42 to 12.2. And you could use math to try to find this problem. But again, if we're dealing with high amp loads like this, I want to load that circuit at the component with a load that's comparable. You know, so let's say, so this takes 4 amps to light. Actually, it takes about 6, but it'll maintain around 4 amps. And that's why it won't light as it's trying to put, that's why the voltage goes away. Like that. And you can see, that's not going to work. So this is a fuel pump circuit that normally draws 6 or 7 amps. I'm not going to test it with this. I'm going to test it with this, because this bulb loads that circuit appropriately. So you don't need to use voltage drop testing if you have either a known good component or you have a known good test light that will load the circuit appropriately. You can skip the end-to-end testing. But this isn't going to be the answer in this case, in the case of a high amp load. This is a 250 milliamp test light, and you can see that it's pretty worthless for this test. I mean, there is some voltage drop across it, but not enough to be useful. You know, so again, you need to really understand what you're doing in order to do the circuit testing, because you need to understand how the circuit works. You need to understand the current that the circuit can carry, and then am I using the appropriate test light if I'm going to substitute the component with a test light. And then you can use just the test light in this case. So I know this component is not functioning. I know that if I measure the voltage drop, I'll put this down so you can see it a little better. I know if I measure the voltage drop across the component, it's less than a volt. It's not enough to light that light. So how am I going to solve this problem? Well, if I have the power probe in my hand and I have it hooked to the vehicle battery, I can simply add a power here, 12 volts off the power probe. I can add it here on my component at the feed and see if it makes a difference. What's cool about the power probe is you're doing all this voltage drop testing without all this stuff. And I've got a few videos floating around out there demonstrating that with the power probe, and demonstrating how we can use a load to measure voltage drop using the power probe. But right now I just want you to understand where the voltage drop comes from, which is a high resistance, which would be nice if they all lit like that, but they don't. But that, with a power probe, you can do all this really quickly, because the Power Probe 3 has a voltage indicator that shows you the difference. Again, the Power Probe has one probe on the end. It's just the positive probe. So you can imagine the Power Probe is this, with this always attached to the battery ground. So then you can measure here and here and get it. So like, say I've got that attached to the battery ground, and I've got my component connector disconnected, and I measure here, I've got 12.38 volts. And I measure here, I've got 0. So now I'm going to measure here, and I've got about 900 millivolts. I'm going to measure here, and I have 44 millivolts, sorry. So if I'm measuring here and I've got 900 millivolts and I've got 44 millivolts here, and I have my negative lead on the ground, which is the lowest potential voltage in the entire circuit, where is my problem? That's simple. I've got higher voltage here, I've got lower voltage here. So I know this has the most potential, that has the least. So I know my loss in potential is here because I'm at 1.1 on the positive. And as soon as I take that off, I have battery voltage. So what happens if I get rid of my high resistance? I'm going to measure here, and I have 11.2 volts. Now, I'm going to add that back into the ground. So I've got that bulb. Well, I'm going to leave that one there, actually. I'm going to add that up here. And you can see that this is going to here. Okay, so this is still my component connector. This is my ground side. And again, imagine I'm using the power probe because I only have one lead here, and my negative lead is going to always be on my ground. So if I'm using the power probe and I just touch it to my positive lead and I have 12.2 volts, I know my voltage drop because I'm measuring at the lowest point, which is the battery ground. The lowest voltage potential in the circuit is at the battery ground. I have 12.2 volts here. So I know my feed side of my circuit is good. But I measure here, and I have 11.17 volts. Well, I have a high voltage on my ground. What does that mean? It means the ground's faulty, right? Or I have a high resistance point between here and my ground. I have something in series causing trouble. So what's going to happen when I get rid of my high resistance point? Light bulb works again, right? And I measure here, and I've got just the normal amount of voltage drop that I would have on a circuit, which is a few hundred millivolts, depending on current flow and ampacity and all that. But I see I have voltage here and there. And again, I'm measuring at the battery ground, and everything else is a subtraction meter. So now that I have this on the battery ground, if I'm using just a power probe, and I'll demonstrate this sometime with just the power probe, but this has to be understood first, because the power probe can be confusing to people that don't understand these concepts. So again, power probe has one lead because the negative lead is always on the battery negative. I'm going to start at battery 12.1. Okay, oh look, I've got a splice, right here, 12.1. This side I've got 12.2, all the way back down to my component connector, 11.97. I'd say that's acceptable. And then my ground side, 300 millivolts, that's acceptable. And my component's working. But if my ground side has a high resistance point that isn't a light bulb and lights super bright, it doesn't even matter. So again, I can disconnect this. My ground for my negative lead for my multimeter is on the ground, battery ground. If I check the feed at my component, I've got 12.35 volts. If I check the voltage on my ground side, so the difference in voltage from the ground terminal at my component to the battery ground right now is 0 volts. So then if I hook up my component again, and then touch the ground, you can see I've got 11.1 volts, and I've got my battery voltage here. So I know the problem is on my ground side, and I don't have to do all the end-to-end testing and a bunch of messing around. It's all right here. But that's the advantage when I'm doing simple circuit testing like this. That's why I use the power probe and a test light, is because the power probe works as a multimeter. There's a voltmeter to measure the voltage, and my test light will load the circuit if there's any question. And again, I'm not going to always use this test light. I might use this as a test light, because if I'm testing at a fuel pump or a fan circuit, you know, a fuel pump circuit can carry the 250 millivolts this light, or milliamps this light will carry, and light just bright, but won't run a fuel pump. That's why we want to use a much heavier load that's about, say, 40 to 60% of the fuse rating of that circuit. That's usually the engineering principles that I go on. Anything over 60%, you're going to risk blowing that fuse over time or compromising the fuse. Anything under, say, 30% of the fuse rating, you may not load the circuit enough to identify a problem if the problem is there. But you can always identify that the problem's there first. You don't need to just jump to voltage drop testing, and that's why one of the reasons I'm making this video is because if you disconnect this component and then measure across, and you've got battery voltage, and then you connect it, hold on here, we'll connect that bulb again. So all you need to know before you do any voltage drop testing is, do I have voltage across the connector at the component? Yep, sure do, right? All right, I've got a voltage that I would expect, and then I'm going to connect the component back up, and my component still doesn't function. Well, I don't know if my component's good or not, but I can, once my component's connected, measure the voltage drop across the component again, and if I don't have near, or within, say, 500 millivolts of the original measurement, I know I have excessive voltage drop on that circuit. And in this case, I have way less. So I went from having 12 volts to less than a volt. So I know I had significant voltage drop in that circuit, and now I can go do my end-to-end testing. That's always the step I see missed in training videos when people try to explain voltage drop testing. Is, first of all, you need to understand that this is a subtraction meter. It's just measuring voltage potential. There could be 12 volts. There actually is 12 volts through here, out here, all the way to here before it lights that light bulb. But what I want to know is the difference across my component, because the difference across my component is what allows the current to flow and light the component up, or allow the component to use that electricity for work. So across here I have less than a volt because that's loaded, because this high resistance is loaded. If I take it off of here and I measure across here, I have a potential of 12.3 volts. With the component loaded, I have a potential of less than a volt, and that's not enough to make that component work. So now I know, okay, I have a high resistance point somewhere in my circuit, and now I need to do voltage drop testing or grab maybe a more convenient tool. If it's more convenient to use the power probe, I'm going to grab that. If it's, if the circuit's really simple like this on the bench, well then yeah, then I can just move my ground to battery ground and then check here and go, hey, I got my 12 volts, cool. And I check here, whoa man, I got 11 volts here. I know my problem is from here to the ground because I should have near 0 volts here, or at least, under, say, a volt, right? And then here, I've got 12 volts, so I know I have the full potential to here, and I still have potential here. So I know that my potential is being lost downstream of the ground, and I have to go that way to find it. So I know I'm kind of beating this to death, but I think it's necessary because voltage drop testing doesn't always apply, but the most important thing is that you find the fastest route to decide, does it apply or not? And to me, once I've verified that, you know, my fuse is good, everything I can visually see about the component without doing any actual work is acceptable, the next thing I'm going to do is gain access to that component, disconnect the connector, and maybe not. Maybe I wouldn't even disconnect the connector. Sometimes, if it's easy, I'll just back probe it and measure my voltage. But a lot of times, if I measure this, you know, say I do, I just go to the component, back probe it, and measure it here, and go, okay, well, I have no voltage. Component's not working. I go here, and I measure across there, and I've got less than a volt. Okay, do I go right back to checking the fuse? Do I go to the ground? What do I do? Well, what I'm going to do is disconnect my component and see if my voltage changes. And it went up. Okay, well, now I know my voltage went up. I either need to take the appropriate test light then test that with the component eliminated, or I need to reconnect it and put one of my probes on a absolutely reliable source of known voltage. And it can be the positive side if that's easier for me for whatever reason. It's cool doing this because I just tangle the hell out of my leads all the time. But maybe it's easier to get to my positive. Maybe the ground is a pain in the butt and I can't get there. So I just put my positive probe over there on my battery positive. For whatever reason, it's easier. And I know I have voltage drop at the component. I'm not getting the voltage I need. So now I'm testing with just my negative. And I'm going to measure here. And I've got 46 millivolts. Well, if I have 46 millivolts measured with my ground lead here, and I know I have battery voltage at my positive lead, so I know I have 12 volts here, and I measure that and I've only got 50 millivolts of drop, I know I have battery voltage here, because I'm referencing battery voltage on this lead. So then if I go to this side, I've only got 900 millivolts of drop across my component. And I know if the voltage is 0 here, or close to 0, I should have a whole lot more than 900 millivolts. You know? So, I know there's a problem, right? Because this isn't measuring what battery ground measures. When I measure ground, it's 12.4 volts. Wow, it would be 12.24 with it loaded, but you can see, so I know I have an issue somewhere on my ground side. So I don't need to go, okay, positive to negative, measure that, 50 millivolts. And now I gotta go access my ground, figure out where that's at, and then go over here and measure the ground. I don't need to do that. I just need to know where a reliable point of reference is. If I know I have battery voltage on my positive lead, absolutely, because I'm measuring it right at the battery, that's good enough for me. I have a point of reference. Now I just need to know the difference and what to expect here. I expect near battery voltage at the positive lead at my component, and I get that. Here, I expect near battery negative, which is near 0 volts, and I check here and I don't, because the difference between the positive lead, which has 12 volts on it, and the ground lead at the component is less than a volt. So I know I have some sort of high voltage still on this circuit, and it's not getting a full path to ground. If it was, I'd have 0 volts here, and I can demonstrate that by touching these together. Or not 0 volts, sorry. I'd have battery voltage here, because now I have 0 volts, but I'm going to measure battery voltage because I have 0 volts on this lead and battery voltage on this lead. And you can see with the high resistance there, I have 1 volt, and that's not enough to get anything done. So anyway, I know I'm beating this to death, and I almost want it to be boring. I want you to get so bored with this that you know it so well that you don't even have to think about it. I don't know, I've bored myself, so I think this is enough. Thanks for watching, I really appreciate it. Have a good day, go out there, fix some stuff. Oh, and if you like this, like, subscribe, give me some more ideas. Anything you guys want to know or you want to get better at, or you want to understand more of the fundamentals. In my opinion, the fundamentals use in an advanced way is more effective than trying to learn advanced techniques. So just understanding the fundamentals will get you so much further than trying to just take advanced classes without really understanding what you're doing. And again, this is all basic tools. This is a multimeter and a test light, you know, all simple stuff. The power probe, I think, can be had for less than $200, which is an awesome tool, but you have to understand all these concepts before you go just cutting loose with the power probe. And the switch on the power probe is 100% optional, and I'd recommend not using it unless you have all of this in your head and you understand it completely. Anyway, thanks for watching. I appreciate it. Please like, share, subscribe, all that stuff. It really helps.